Hello, welcome to Econometrics Melody. In this video, we'll discuss about the role of constraint term in regression. So in our preceding video, we had seen that the beta estimate of partition regression, they are calculated by partitioning out the effect of some independent variables from other independent variables as well as the dependent variable, and we run the OLS regression. And in order to partial out the effect of one variable or variables from other variable or variables, we take help of the error maker matrix, because the residual, generally the OLS residual partials out the effect of x and provides that portion of y which has no influence of x. Similarly, for an individual or a single variable, we calculate the coefficient making use of same principle. First of all, we partial out the effect of the independent variables from that individual variable, as well as we partial out the effect of other independent variables from the dependent variable as well, and then we run OLS regression. And in these cases, actually we are running the residual of the dependent variable after partitioning out the effect of the other independent variable. This is going to act as our dependent variable, and the independent variables are those independent variables from which we have partial out the effect of other independent variables. So this is the basics of how we calculate the beta coefficient for the partition regression, and this is the residual when we partial out the effect of variables in matrix 2 from the variables in matrix 1. Then after we run the regression of EY2 on E12. So vector I, it represents the column vector of ones, and the sample size n is given as I transpose I. Summation x can be calculated as I transpose x, and x bar, we know the formula. This is the summation x divided by n in matrix or vector notation. It is I transpose x divided by I transpose I, and this can be also written in the form of regression beta coefficient is I transpose I inverse I transpose x. This is the OLS estimate where x is our dependent variable and I is our independent variable. Now the deviation from mean, if factor x it is equal to 1 2 3, the mean is 2. Now we want to calculate the deviation from mean, and this is our general notation, and in matrix or vector notation we write it as the observations minus the vector of mean. So this is equal to 1 2 3, and let us take the mean common, so we are left with 1 1 1 and the constant mean. Now let us represent the result in terms of vector notation. So this is our vector x minus the column vector of 1. This is represented by I, and 2. This is the mean. So it is x bar. This is again equal to x minus I and the mean. And in vector notation, the mean can be calculated as I transpose x divided by I transpose I, and which we have seen already. Now let us take x common in the post multiplication side. So we are left with I minus I transpose I. If we represent this term as deviation from mean matrix, so let me write it as M0x. So here also let me write it as M0, where this notation this provides the deviation from mean. So this is called as deviation from mean matrix. And if we post multiply to this matrix, if we post multiply any matrix or the vector, then we get the vector or the matrix of deviation from the mean of the respective variables. So the deviation from mean matrix, this is going to be useful for today's topic. And with reference to the partition regression equation, we can calculate the value of beta 0 and b. And here we have partitioned the independent variable of x is the column vector of 1, and here this x contains all other independent variables, and this I is the indication or place for constant. So here this I is a vector while x is a matrix, and beta 0 this is a scalar, where beta this is the vector of the scalars. Now let us calculate the value of beta 0. So beta 0 this is equal to Similarly, we can calculate the value of beta. So this beta, it contains the coefficient for all other independent variables except the constant term, and making use of partition regression beta estimate, we can calculate it as X transpose, and let me call it as Mi, the error vector matrix associated with vector I or the variable I, and we are trying to partial out the effect of I over here. So this inverse and X transpose Mi. So basically, we want to say that Mix, this is the deviation from mean for the respective variables, and Miy, so this gives the deviation from mean of the dependent variable y. And actually this beta is the OLS beta of regression, taking the deviation from mean of each of the variables. So now we want to prove that actually this EMI, this is the deviation from mean maker matrix. So we want to prove Mi, this is actually the deviation from mean maker matrix, and the value of Mi is given over here. And let me write it once again, and I'll prove that, and we will prove that. So this is equal to I minus I, and this is I transpose I. This is actually a constant. So let me write it as n to the power minus 1, and I transpose this is equal to I minus, and as it is constant, so let us take it outside of these vectors, and n inverse is 1 by n. So this is n, and I minus I transpose, and n is written as I transpose I, and we know this expression, and we have already seen it, that this is equal to the deviation from mean maker matrix, and is Mi is equal to the deviation from mean maker matrix. So these are the deviation from mean. So we are taking the deviation from mean of X, and we are taking the deviation of mean from Y, and we are running a regression. So having a constant term in a linear regression equation, this is equivalent to running a regression with a deviation from mean of the respective variables. And let us see the working of this principle by the help of example in this data. So our dataset, it contains 21 observations, and let us create our dependent variable as well as the independent variable. We have 4 independent variables, and let us create the deviation of the dependent as well as the independent variables. These are different variables. Now let us run the general regression equation where y is our dependent variable and x is our independent variable. So in this regression, we have a constant. The value is 115.75, and these are the beta coefficients for the respective variables, independent variable. Now we are taking the deviation from mean of the dependent variable is the dependent variable, and the deviation from the mean of the respective independent variables is the independent variable, and we are going to run a regression, and let us see the result. So the constant term in this case is equal to 0, but if we compare the beta estimates for the respective independent variable, they are one and the same. So let me display the comparable results, and for the normal variable, that is without their deviation form, the value of constant is 115.75, and when we take the deviation of the dependent as well as the independent variables, and if we run a regression, then the beta estimates are same, and the constant for the regression in the deviation form, this is equal to 0. So actually the constant, it is transforming the dependent and independent variables into their deviation from mean form. So this is a very important implication. In this case, our beta 1 is equal to alpha 1, and beta 2 is equal to alpha 2. Running a regression with constant and without constant, they are completely different thing, and the constant term actually it transforms the variables into their deviation form to calculate the value of beta estimate. This is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.